What's going on, everyone? I'm back with another video. The good news is, or I guess the difference or subtle difference, is that I'm finally back in my dorm. So hopefully I can start recording a lot more. And also I don't have to worry about any background noise, and then also like finding the time to do it. If you would have paid attention to my last couple videos, I was able to record them at my house, but the only exception was it was pretty much late in the evening, so that's why my voice will sound like it's tired or probably bored. It was usually because I had to keep my voice down, or it was kind of like in the middle of the day and you could faintly hear some background noise. Hopefully, not much of it went through the microphone, but other than that, I actually now have the proper setting to actually make these videos the way I wanted to. But yeah, that's just a quick little update. And so now we're going to discuss, well, before we discuss about the block case for the last example of determinants, I did mention in the last video that there was going to be another way that we can do the square reduction. So in the first, or I guess in the previous example, we did it with just the first row, and I mentioned that we're going to do another one with just using the third column, and how I said it, this one's much better because of the zero. And if you paid attention to the example that we did, we multiplied each number in the row, and so you can see why the zero would be very helpful, because if the zero was there, this second portion, which is all equal to zero. But we're just going to go ahead and do that quick little example before we do the last case, and as well as review the expansion method. As you can see, and also like in the last video, it does look kind of messy. So I'm going to try to like re-explain it real quick, and hopefully it'll make much more sense. So for the first one, we're just going to go ahead and redo the square reduction example. And so gonna paste it again. Okay, so for this one, like I mentioned, we're gonna be using the third row, and so if you recall on how to do it, you just go, you can technically use, you could go from like top to bottom or bottom to top. It doesn't really matter what order you do it, but as long as it's an order that is consistent throughout your work. So for me, I always use top to bottom, and we're just gonna go ahead and get into it. So for the first one, we obviously have to multiply it by 8, and then we take the determinant of this smaller matrix, because as like I mentioned before, we ignore everything that this 8 it consists of. So that means both the row and the column. And so 8 is in the first row, but it's also in the third column, so we completely ignore those. And so our new matrix would be everything that's not being ignored. So it'll be 3, 4, 6, 2, and take the determinant. And then this portion here, the next one is just going to be 0. So this just goes to 0. It's just straight 0. So that means we could just only take the determinant of just 2 matrices instead of 3, which is really helpful, because you reduce the chances of making an error in your arithmetic, but also means you do less work. And so the last one is just going to be 1, and then you multiply it by the remaining matrix. So the third column gets ignored, and it's also in the third row, so that gets ignored. So we're just left with determinant of 1, 2, 3, 4, and then you just add them all together, and you should get the same result. So this would just be 8 times 6 minus 24 plus 4 times 1 minus 3 times 2, which is 6. And so that's going to be 8 times negative 18 minus 2, and you should still get what was it, negative 146. Double check. Yeah, negative 146. This should, yeah, because this would be negative 144, and this would be minus 2. So yeah, that's much more faster way because we just have to do one less multiplication and I guess subtraction. Because I mean we have to find the determinant of 2 by 2, but it becomes very useful if you have a higher dimension matrix, like a 5 by 5, and let's say that in one of the rows it consists of 3 zeros, so we could just use that row, and we'll only have to end up taking the determinant of just 2 terms or 2 4 by 4 matrices, and then hopefully by then it becomes much more easier, or more specifically it becomes less work than what you usually have to do. And then so before we get into the last example, I'm just going to do a quick overview on the expansion method. And so when we have a 3 by 3 matrix, what you to find the determinant, what you have to end up doing is add in 2 more columns, in which the fourth column would be the first column, and the fifth column would be the second column. So you're just copying them, and then what you're going to end up doing is you're going to take the diagonals from top left to bottom right and multiply them out and add them together. So this would be one diagonal, this would be another diagonal, and then this would be the other diagonal. So we'll have 1, 2, 3 diagonals because they each have the 3 elements. If you would have done this one, it will only have 2, so you can't really multiply it. And same thing goes from the others. So that'd be 2, and then obviously the other one's 1. So you'll have the multiple of the first one. So it'll be A, E, I, and then B, F, G, and then C, D, H, and then you add them all together. And then what you end up doing is that you have to subtract the other diagonal. That's going to go from bottom left to top right. And so it's going to be bottom left to top right, these 3 elements, then these other 3 elements, then these last 3 elements. And so it'll just be G, E, C, and then H, F, A, and then I, D, B. And then you also add all of them together, and then your answer should just be the determinant. So in short, you multiply each diagonal and add them together, and then you subtract it from another set of diagonals that also have been added together. So if we were to have this minus sign distributed, we will just have negative, actually let me use a different color, a negative GEC, negative HFA, then negative IDB. And of course, some of these can be positive if there is a negative number involved, but that's just very situational. In this case, each element here is just any real number. So now we're going to talk about the last method that I've been holding on for so much, and that will be the block method. And so what I mean by the block method is, so if we have a 4 by 4 matrix, as we have here, we can break this up into smaller matrices, 4 blocks. So we can make 4 2x2 matrices, and so we're just gonna label them block A, B, C, D. And so what ends up happening is the determinant, which is equal to the determinant of the product of block A times D minus B times C. And notice how this is very similar to when you take a 2x2 matrix where it's AD minus BC, and these are like the elements. It's the same thing, the only difference is you're taking blocks. So you're basically essentially multiplying two matrices together and then subtracting the product of the other two. However, you can only do this if C times D, block C times D, is equal to D times C. Now, this portion is a big deal because if you recall from matrix multiplication, matrices are not commutative. So that means this condition is really hard to satisfy. But we did discuss about a specific matrix where this is true. And so this will only be true if C, or it won't only be true, but this could be true if C or D is equal to the identity matrix. And if you look over here, block C is the identity matrix. So we could go ahead and do this method. And so what you're gonna end up getting will be, this would equal to the determinant of 3, 6, 10, 8 multiplied by 9, 4, 6, 3, and then you subtract it by the other two terms, these two, and so that will be 18 to 12, 0 multiplied by 1, 0, 0, 1. And it has to be in this specific order because, as I mentioned before, matrix multiplication is not cumulative. So you can't flip the B and the C or the A and the D. No, it'll just give you a different number. And so when you do the math, it's gonna get you to negative 108. And you can double check by finishing off this exercise, or you can do the square reduction on this 4x4 matrix. If you decide to do the square reduction, which I highly recommend just for practice, I recommend doing it across this diagonal. Let me actually use a different color. Across this diagonal. And the reason is because you have 1 0, 2 zeros across this diagonal. So all you really have to do is just take the determinant of 2 3x3 matrices. And then what's good about that one is that 3x3 matrix will still contain those two zeros, so it'll make your life so much easier with the work, and you should still get the answer that I got, which would be negative 108. And yeah, that is all for matrices. This concludes the chapter of determinants and matrices. And so now we're going to move on to our next subject, which would be, or not subject, next topic, which would be vector space and subspaces. And boy, oh boy, it's going to be quite an interesting ride. But until then, I'll see you in the next video.